Welcome to Lecture 4. Our goal still hasn't changed. We're still interested in solving counting problems. And there's a lot more that could be done with the combinatorial techniques like double counting and bijections that we used last week. Instead, we're going to start building an algebraic machine. And to make all this work, we need to think about power series. I'll be a little more formal about this later on, but for now, by power series I just mean an object which looks like this. It's a sum of a constant term, a real number times x, a real number times x squared, and so on. For most of the power series we'll be looking at, it's useful to think in both sigma notation and in a more expanded form, so I've written both here. When you see a power series like this, it might be your instinct from calculus to ask whether it converges, or what its value is at some particular x. In combinatorics, we're not concerned with either of those things. We'll simply be manipulating these objects on a purely algebraic level. Here's a simple calculation where we add two power series after multiplying one of them by 2x. Here's the same calculation using sigma notation. It's important that you're comfortable with both notations. Note that in the first line, I re-indexed the range of summation in the second sigma so that the powers of x lined up. I won't be focusing on details like this in the future, but it's important that you're able to do them. If you think two sigma expressions are equal, but you're not 100% sure, it pays to write them out longhand and see if you're right. Now we'll look at another example where we multiply two power series. Let p of x be the series 1 plus x squared plus x cubed, and so on. We're going to multiply this by the series 1 minus x. We expand this out using familiar algebraic tricks, and then we combine like terms to compute the coefficients. We see that the constant term is 1, and all the other coefficients are equal to 1 minus 1, in other words 0. Therefore, the product of these two series is just 1. Since they multiply to make 1, we think of the series p of x as being the inverse of the series 1 minus x, and we write p of x equals 1 over 1 minus x, or 1 minus x to the power of minus 1. This may be familiar as the formula for the sum of a geometric series. It's important here, though, that we see it as a statement about power series rather than a statement about real numbers x. Here's the same calculation done purely using sigma notation. It takes up less space as well as being a little more rigorous. Here's another theorem about power series that you may have seen, the binomial theorem. It tells you how to expand 1 plus x to the n, where n is any non-negative integer. It says that 1 plus x to the n is equal to the sum of n choose k x to the k over all k between 0 and n. The statement explains why we call the numbers n choose k binomial coefficients. It also points to a link between algebra and combinatorics. The term on the left-hand side is completely algebraic, but the terms on the right-hand side are things that we know have a meaning relating to counting. There's more than one way to prove this result, and the proof that we'll use is different from the proof in the notes. We'll be using induction on n. The base case just says that 1 plus x to the power of 0 is 0 choose 0. This is true. Now, to apply induction, we're going to assume that n is bigger than 0 and that the theorem holds for n minus 1. That is, 1 plus x to the n minus 1 is the sum of n minus 1 choose k x to the k for all k between 0 and n minus 1. This is the inductive hypothesis. The rest of the proof is a calculation, which you can see here, to prove that the theorem is true for n. I've written out every step, but if you're comfortable with some of the easier ones, it's okay to leave them out when you're writing a proof like this. There are two main ideas here. The first is that we write 1 plus x to the power of n in terms of 1 plus x to the power of n minus 1, so that we can use the inductive hypothesis. The second is that we used example 1.7 from lecture 2 to simplify the sum of two binomial coefficients into a single one. We have n minus 1 choose k plus n minus 1 choose k minus 1 is equal to n choose k. The proof also involves combining different sigma expressions. So when reading it, you should pay attention to where the indexing changes are happening and make sure that you understand them. Of course, if you can't see why two sigma expressions are equal, write them out with dot dot dots and see if that helps. Here's the same calculation, but performed without sigma notation. There's nothing wrong with it, but hopefully its length shows you why sigma notation is often preferable. I've already mentioned that when dealing with these power series, we don't have to worry about convergence. But it's reasonable to ask how I can get away with this. The answer is by not claiming that they're functions of x at all. In fact, when I write down a power series, finite or infinite, what I'm talking about is a different type of object called a generating series. A generating series is by definition an expression which looks like f0 plus f1x plus f2x squared plus f3x cubed and so on, where the f's are all real numbers. These might look like the power series that you'd see in calculus, but in fact the way we think of them is more like a sequence of real numbers, or a vector. You can think of the pluses and the powers of x as punctuation to distinguish the terms of the sequence, just like you would use commas to distinguish the coordinates of a point in Rn. I've used a different color to indicate the pluses and the powers of x to emphasize this point just for this lecture. The information that the generating series contains is really the sequence of coefficients. Generating series are also known as generating functions or formal power series. There's a famous textbook on generating functions by Herbert Wilf, and the first sentence in the book is that a generating function is a clothesline on which we hang up a sequence of numbers for display. This is a great way of thinking about these objects. The coefficients are what matter. That said, there's no reason to worry too much about all this formalism. If you want to add two power series, you'll add them in the way you expect, treating them like polynomials. If you want to multiply them, you multiply them like they're polynomials. However, sometimes it can be easier for students to actually multiply two given polynomials than to figure out how polynomial multiplication works in general. Here's the formula. Even if this looks new, then playing around with some examples will show you that this is in fact the way you've always multiplied polynomials, just extended to power series. Here's what these definitions look like if I don't use sigma notation. And here's a quick example of applying the formula for multiplication. You can see that if you do this without sigma notation, you start getting into dot dot dots where it's not clear at all what the pattern should be. For those of the fans of abstract algebra, the fact that we can add and multiply generating series implies that they're a commutative ring. They're also an infinite dimensional vector space over the reals. Earlier, we saw a pair of generating series whose product was 1. It's useful to have some terminology for this. If f is a generating series, and g is another generating series so that f times g is equal to the generating series 1, then we write that g of x is the inverse of f of x, or g of x equals 1 over f of x. The example we saw earlier is that the series 1 plus x squared and so on is equal to the inverse of the series 1 minus x. Not every generating series has an inverse. For instance, the series x plus x squared and so on will have no inverse. You can show with some linear algebra that the inverse of a generating series f exists if and only if the constant term of f is non-zero. As we stated it, the geometric series only told us the inverse of one particular series, but in fact you can use essentially the same idea to compute the inverse of many other things. The idea is to use multiplication and substitution to make what you want to invert look like 1 minus something. Once you've done this, you can apply the geometric series formula. Here's a few examples. Thank you for watching. That's all for today.